or have office hours. So use this time to read your text, because magnetism can be pretty tricky. All right, so we've seen a couple things, and I'm not going exactly in order here. We're mostly in chapter 12 right now. We're going to go back and pick up a couple things from chapter 11 that I think are going to be easier to grab onto now that we've seen some stuff from chapter 12. So what we have hopefully figured out, and you will have homework over magnetism that gets up today. We do next week. What we figured out from class, from your book, from your lab recitations yesterday, where your TAs presented new material, is that currents produce magnetic fields. So, just to really quickly run through the Biot-Savart law. Have a current. A steady current. It doesn't have to be steady, but I'm going to tell you it's steady. And I'm going to pick out a little section of this. I think we went from A to B. Right? I'm picking out a small section, not because I have to, but what I want to do is have all the nice, pretty vector cancellation that we get from symmetry. So I'm going to let this be a really, really long wire, and I'm just looking at a little section of it. So all the components are going to cancel like I want them to. That keeps you from having to even worry about it. And we picked out a point. I'm going to use D. I think I used A in class, bad plan. I'm going to use some distance D away. And we formed some small dx, but we had to make dx a vector. Right? Because the Biot-Savart law is going to use a cross product. And so I need to formulate my path as a vector. So here, it's horizontal, so I'm going to pick out dx. And then to make that a vector, I just put on the I hat, right? That doesn't change anything because it has a magnitude of 1. It just gives it a direction. Of course, if my wire takes a turn, I don't have to use something else besides that. But in this simple case, it doesn't. It's all in the x direction. So I'm going to pick out I hat. And from that little dx, which is carrying a current I, I've got this distance r, which according to my geometry is x squared plus d squared square root, same as it has been. And then, in addition to that, I need to have a vector pointed from my source to my observation along that line. So it just goes right up the line which I've labeled r. This is a unit vector, which I'll call r hat. Right? And I need this because the Biot-Savart law is going to use these two things. Once I have all that in place, the Biot-Savart law says this. Magnetic field is equal to mu naught over 4 pi integral of I dl cross r hat over r squared, where I is my current, dl is my path. R hat is a unit vector pointing from this differential path dl to my observation points, and this is the distance between them, right? This is my general form. To make it specific to me, I'm going to replace dl with dx I hat, right? dl is just my placeholder for my differential length. My actual path is along the x-axis, which leads to dx. To make it a vector, I just slap on the I hat. So dl will become this. R will become this. This is my distance, x squared plus d squared square root. In this case, I've told you that I is steady, which means I can bring it out of the integral. So once I put all that stuff in, I get this expression, mu naught I over 4 pi. And then integral, it's a definite integral from a to b. dl gets replaced by dx I hat cross r hat over x squared plus d squared. Now, any questions how we got here? Next step I want to do is take care of the cross product. Right? If I can get rid of that guy, the integration will proceed a little bit more straightforwardly. So let's just do some side work. I hat cross r hat, by definition, means magnitude of I hat times the magnitude of r hat times the sine of the angle between them times a normal vector, normal to both I and r, perpendicular to both of those guys. So let's take care of that first. Do we all agree that I hat and r hat lie in the plane of the board? Yeah. So the only way to be mutually perpendicular is to either come out of the board or go into the board. The right-hand rule will tell you which one, right? Fingers in the direction of the first vector, and this is where remember, vector multiplication is not commutative. Order matters. Fingers in the direction of the first one. That's I hat, straight this way. Curl them towards the second one. That comes up like this. Stick out my thumb. That gives me a vector out of the board, right? So if I just to indicate that to myself, I'm going to put that. We need something to call it, and we're used to I being X and J being Y and K being Z. So let's just call it K hat. Right, so this is going to become a K hat. Now the question is whether or not it's positive or negative. There are conventions about that. I don't really care, as long as you define them and stick to them, right? Let's just call it positive, being out of the board. I don't really care, right? You've indicated the direction to me. That's all I care about. Okay. So now, let's take care of the rest of it. What is the magnitude of I hat? And what's the magnitude of r hat? Unit vectors always have a magnitude of 1. That's what makes them unit vectors. What is the sine of theta? First of all, what's theta? Theta is rigorously defined here. It's defined by the definition of the cross product. It's the angle between the first vector and the second vector measured counterclockwise. That has to be right there. First vector to the second vector, counterclockwise. First to the second. All right, by my geometry, what is the sine of theta? D over r. Right, the geometry comes to your rescue there. R, of course, we're going to express as x squared plus d squared square root. So when I put in that cross product, here's what I have. And I'll move this back up so you can see it. U naught I, K hat, constant or no? Constant. U naught I, pull that out, K hat, over 4I. Alright, that's pulled out the constant. Not all unit vectors are constants, but K hat is. All of them are constant in magnitude, and not all constant in direction. K hat is. Cartesian unit vectors are all constant. Integral A, B. What do I have left here? Well, I have dx, and then the cross product. The only thing that the cross product has left me with is the sine of theta. And K hat, but already took care of that. So d over r. Dx, and that's d. And then r is just x squared plus d squared square root, which I already got 2 of those guys here. A third one is going to give me this, x squared plus d squared. All of that to the 3/2 power. We've seen this before. D is a constant, of course. Pull it out. And that's what I'm left with. And that's an integral we've done before. We saw this in letters. So this integral is valuable using tables or trig substitutions if you really just love it. Feel free. But that's as far as I'm going to take it from here. Now, okay, questions? Any of this? When you put in infinite limits, right? So I gave you this as a definite integral from A to B. When you put in other words, when you let A to B go off to infinity, you get the standard formula for a long straight wire. Long tells you you're going to treat it as an infinite, right? It's not infinite, but we're going to assume that we're staying away from the ends or any curves so that we can treat the magnetic field in this region as infinite. You get this. as it gives it. Now, your book actually doesn't give you the theta hat, but we'll talk about that. They do, but it's not in the highlighted section. So all this is the result of this when you integrate over infinite limits. You can probably see what's happening. I've got an even function over symmetric limits. So I'm going to probably integrate from 0 to infinity and multiply it by 2, which is how that 4 turns into a 2 here, right? We've got pi, 4 pi, and 2 pi come from geometry. The r, in this case, is the distance away from the wire in which you find yourself. I don't really like the fact that they used r, but that's okay. So the capital R is a constant here, but it tells you how far away from the wire you are. Now, what about the theta hat? Well, we started to do this last time. What I've done here is to find that the field in this orientation is coming out of the board. So let me draw that for you. Let me shift my perspective to over here, and I'm going to look down the wire. Right? As I'm looking down the wire, at the point which I've drawn up there, the field is coming out of the board. So let me draw that. Here's my wire carrying the current. I is coming right at you. And at this position here, I found that the magnetic field looks like this. Right? Now, what I'm going to do is shift my perspective again. Sorry, this is what I call the distance d. Right? I'm going to shift my perspective. I'm going to rotate my head. Right? Rotating my head doesn't change the wire, doesn't change anything about the physical system. I'm just shifting my perspective. When I do that, right, this is what it looks like. Looks like that. Okay. Now, from my new perspective, let me do this again. Right? Look for it, the field right above it. Right? So I shifted my perspective, and now I'm reworking this problem. Hopefully we can all see that what we're going to get is that again. Right? Now shift it again. Tilt your head again. This one is now here. This one is now here. And rework it again, and you get this one. Right? See what's happening? So let's generalize. Right? I'm just picking out points, a distance d away from that wire, and I find that the magnetic field is always tangent to the circle that I end up describing. Right? That's where the theta hat comes in. The k hat was nice in this one perspective because it let us pull it out of the integral. Now, we're going to just do some thinking about it and figure out that if that's the case, then the magnetic field is tangent, or I should say, it's perpendicular to a radius, but the collection of all lines perpendicular to radii are tangent lines. Right? That's the definition of a tangent line. It intersects a circle at one point, perpendicular to the radius. So, if I were to draw the magnetic fields here, I should say, no, the field lines, right? Remember, the field is a vector at any point, but the collection of those vectors is a field line, right? Not a vector itself, it represents vectors. I'm going to find that they form concentric circles moving outward from the wire. So here's the wire and here's the field. So this is what I found the magnetic field was at some particular r. We can generalize this to the general formula by erasing the uppercase r and just saying, well, that's my variable now, right? For any given r, any given distance away from this wire, the field will be given by that. So 1 over r dependence is the same as we saw from a line of charge for the electric field, and for the same reason. As you get farther away, more of the field, more of the current comes into view, quote unquote, and cancels. The geometry will cancel one of your r's, so you don't have an r squared. You have a 1 over r dependence, and they form concentric circles. Okay. Now we got here from bios of art. We did a simple, reasonably simple integral in one position, and then did a lot of thinking and generalized that result to this. So, are we all here? Are we all okay here? Now here's the shortcut, okay? Let me introduce you to the right-hand rule for fields. We know the right-hand rule for forces. It's the same as the right-hand rule we did for the cross product, except we have to worry about charges. Right-hand rule for fields, right? We again make a difference between our thumb and our fingers. Our thumb is going to go in the direction of whatever is straight. Our fingers are going to go in the direction of whatever is curved. Okay? For a long, straight wire, what about the system is straight? Hopefully the wire, we all see that, right? So take your thumb and put it in the direction of the wire. I should say in the direction of the current, because the direction of the wire could be the direction of the current. Now your fingers wrap around the wire. They tell you what the field is doing. So the field from this wire is forming circles around it. Above the wire, they come out of the board like we found here. Below the wire, they're going to go into the board, right? I can't draw it in 3 dimensions, but you can kind of see what's happening. Up above there, that's this guy here coming out of the board. Down below, that's this guy going back into the board. The plane of the board is right here. Because remember, I shifted to look down. Okay. So that's the shortcut that gets you there. Thumb in the direction of the current. That's straight. Your fingers will tell you the direction of the field. And this gives you the field. Now, do I expect you to be able to work a biosmart law? Yes, I do. Right? Once I'm convinced that you can just go here. Right? This comes from biosmart. Any questions about that? All right. There's another geometry to look at. And then that will lead us back to what we need to finish up from chapter 11. And that is the fact that I don't have to form my wires in straight lines. Well, let's do this. Here's a really small section of a straight line. Carrying a current that way. What is the magnetic field at that point? Or what direction is the magnetic field going to be at that point? Into the board, out of the board, up, down, left, right, north, south, what? Out of the board. Yep. All right. What about this section of a straight wire? What is the magnetic field going to be at that point? Out as well, right? Fingers the direction of the field. Sorry, thumb in the direction of the current. Fingers tell you the field. Okay. What about this one? Out. You see what I'm doing, right? Little bitty sections of this straight wire. Again, that's terrible. Wow. There we go. Little bitty sections of the straight wire arranged like this are going to give you this field as long as we're at the same distance from each of them. That's out of the field. What I'm doing is I'm saying, okay, if you zoom, if I take a loop of wire and I zoom in close enough on any particular section, it's practically a straight line. Right? So the biosmart law tells us that from each of these lines, I get this field here, as long as I'm the same distance away from all of them. That's just out of the board and same strength. Well, what about now if I just make it explicit? If I have a loop of current at the dead center of this thing, I get a field that is out of the board. What's happening is I'm getting cancellation in all the different directions, except for the outward direction. So at the direct center, I get a field that's out of the board. This is some current I. Now, I'm saying in the direct center, and that's important, because if I'm not at the direct center, it does not look so clean, right? You can imagine if I take this loop and draw it kind of on its edge, so just take your loop and tilt it a little bit so you're looking down at an angle, right? What we're saying is in the center, I've got this field that looks like that. That's what I drew. But as I get closer to the wires, of course, it doesn't work like this. Really close to this wire, I still find a little bit of loops, right? Just like I did for bias apart. If I'm thinking of this section as a straight line, I get little loops of field around it. So what's happening here is I'm getting loops, field lines that form loops that look like this. But at the direct center, I get all the cancellations. See, look, I've got a component this way and a component this way that are going to cancel and leave me with only a net field that is directly up. Now, if I get away from the center, I don't have that lovely cancellation. But in this class, we're going to stay mostly to the center. I want you to know what it looks like. I want you to know that you have to stay at the center. But as long as you do that, the bias-apart law in this case gives you this really interesting result that you get a straight field in the center of a loop of current. All right? Let's apply our new field, right-hand loop fields here. Here's a loop of current. Again, looking at it somewhat edge-on. What's curved here? Well, the current is curved. Take your fingers, wrap them around what's curved, and stick your thumb up. That tells you what's straight. The field, in this case, goes up. If the current was running the other direction, I'd have to wrap them around like this, and then it would go down, right? So flip the direction of the current, flip the direction of the field. Okay? Question about that? This is all directly derivable from bias apart. That is in your text, and you should go through it. It will probably show up on your homework. But again, once you have it, you can just go right to this result. Yep. And what do they use here? They use a J hat. Maybe. What is this? How do we interpret this result? Well, number one, notice that it's very similar to the field of a long straight wire, except I'm missing the pi. That comes out of the geometry. In this case, R, this is why I don't like it that they used it in the other one. R is the radius of the loop, right? So this is a really specific formula for really specific geometry, so just be careful with that, right? The J hat, in this orientation, that probably makes some sense. What this is, it doesn't have to be a J hat, of course. It really is an N hat. N, normal to what? The plane of the loop. So every loop, by definition, will form a plane. This one is like this. Normal will look like this, which is this is how I would draw that 2 dimensions. Your book gives you a J hat, but you just need to understand that's a placeholder for however you orient your loop. If your loop is vertical, N hat will look like an I hat, right? But as long as we understand that, it's okay. Questions on any of that? Okay. Now that we have that in our pockets, we can talk about